Okay, so I'm going to prove one of the law of cosines, which states that if triangle ABC has lengths ABC, representing the lengths of the sides opposite of those angles, right? A is opposite of A, B opposite of B, and C opposite of C, then A squared equals B squared plus C squared minus 2BC cosine of A. Now, since I want this cosine of A, I need to draw um, an altitude. So I can do that from vertex B. So I'll draw an altitude from vertex B, and I'll call it a BD. So let me go ahead and start my proof. So proof, draw altitude BD. Now I can find cosine of A. So cosine of A is equal to, so remember cosine is adjacent over hypotenuse, so it'll be AD over C. And if I were to solve for AD, it would be AD is equal to C cosine of A. Okay, so now in my formula that I'm trying to derive, I see that there's an A squared. So if I can think about the Pythagorean theorem for a second, I know that CD squared plus BD squared is equal to A squared. So maybe I can use that knowledge in order to figure out that A squared and reduce some stuff to get the right-hand side of this equation. So as you can see, I have AD, which is not CD, but I can easily get CD from knowing AD, right? So CD is equal to this entire length B minus AD, right? And I figured out what AD was before, so CD is just equal to B minus C cosine of A. Now, for my Pythagorean theorem, I want CD squared plus BD squared equals A squared, right? So what I can do is I can use sine of A in order to find BD in terms of this side length C, right? And of course sine. Okay, so I know sine of A is equal to, so sine of A is equal to opposite, which is BD, over hypotenuse, which is C. So BD over C. And of course, I want to solve for BD, so this implies that BD is equal to C sine of A. Okay, so now, by the Pythagorean theorem, I know that A squared, right, the hypotenuse, is equal to CD squared plus BD squared. Right? And I know CD in terms of B and C and cosine of A, and I know BD in terms of C and sine A. So this implies that A squared is equal to, so CD squared is B minus C cosine of A squared plus BD squared is C sine of A squared. So now doing some basic algebra, I know b minus c cosine a squared is just b minus c cosine a times itself. So if I were to do that math, I would get b squared minus 2bc cosine of a plus c squared cosine squared a. And then of course c sine a squared is just c squared sine squared a. Now I'm really close to my formula, right? I have a squared, b squared, and negative 2bc cosine a, right? A squared, b squared, and negative bc, hello, negative bc cosine of a, right? So here, what I can see, so this implies that a squared equals b squared plus, so I'm going to put c squared sine squared a plus c squared cosine squared a, and then minus 2bc cosine of a. Now, remember, the Pythagorean identity states that sine squared of an angle plus cosine squared of that same angle is equal to 1. So what I can do from both of these terms is factor out the c squared. So a squared is equal to b squared plus c squared times sine squared a plus cosine squared a minus 2bc cosine of a. And doing this, I can see that sine squared a plus cosine squared a is just 1. So using the Pythagorean identity, I know a squared is equal to b squared plus c squared minus 2bc cosine of a, which is exactly what I wanted to prove.